No, now the little red line is actually moving. Let's see if it, now the red line stopped. Let me make sure maybe it's a YouTube issue or something.
Yeah. Naomi, do you work in building 34?
I do, yeah.
Cool. I used to work on the first floor, sort of by where the SAM test bed is. So
nice.
I got I'm representing today. So
nice. Yeah, I'm not in the office today, but yeah, it's I'm on the second floor. I just got a new office, which is like a corner office, which is nice, but it's like shared with like 5 other people. But I had to beg for a year and a half to get this office because I was like, I don't.
Good. Well,
in Europe we don't do windowless offices. It's like not the policy.
It's crazy. It's crazy that they have such a new building like that, and then you still have interior offices. It's like, but
right. Yeah, I wasn't expecting that when I arrived. So yeah, I've been begging for a whole year and a half, and now I finally have a corner office. It only has one window, but it is a window, and it looks out onto grass, which is amazing.
Good.
Highly underrated to have the sky visible from your office.
Right.
What did you do at Goddard?
I did I was there during undergrad as an intern, working on the SAM test bed and doing some stuff with Curiosity rover, and then I eventually moved on to work with Heather Graham on a laboratory for agnostic biosignatures stuff.
Oh, nice.
Yeah,
I've seen Heather Graham around places. I don't know. There's so many people there. I still haven't learned many people's names.
Yeah, Heather's hard to miss though. She's always got a different color of hair going on every month. So
for sure.
Well, I think we might be yet another failed connection to I got I'm so excited to be your first successful connection, and I think I jinxed it because now it's just set on this red thing and then it times out. So all right.
It says in the corner that it's live.
Yeah, but I think it like goes, it actually did record a little bit live. So it's like doing it but then crashing.
Right.
Oh no, it's working. It's totally working.
See it on YouTube.
Sure, because I did that and then it was only 60 seconds. Are you sure it's actually really staying on?
We'll see, but it looks like it's been going for like 2 minutes and 45 seconds. So I think maybe if we leave it, it'll keep going.
All right.
So the one I see says that it is live currently as we speak too.
Really? 60 seconds. One I see says maybe it's live. All right. Well, I'm not going to touch anything. Okay. All right. Well, hopefully. Okay. So people are joining. I see people joining. Great. Okay. Then I'm probably going to fade away into the background and let all the fellows who organized this take over.
Thanks, Jennifer.
Okay. Thank you. Looking forward
to so we have a minute to go, and once we get to 11, then I will it's 11, so I will start and I'll introduce Dr. Naomi Rowe-Gurney, who is a planetary science postdoctoral research associate at the NASA Goddard Space Flight Center. She's employed by University of Maryland College Park on CREST 2, and she's working with the James Webb Space Telescope. And she obtained her PhD in 2021 from the University of Leicester in the UK. And her thesis was using archived data from the Spitzer Space Telescope, studying thermal structure and composition of the middle atmospheres of ice giants Uranus and Neptune. And she used the retrieval algorithm Nemesis and built a consistent retrieval framework for ice giant planets ahead of the launch of JWST. And she was a member of the Scattered Light and Moving Target Commissioning Team for James Webb and continues to work with the data from the telescope. And she also leads a Hubble Space Telescope program designed to support ice giant observations with James Webb. And throughout her PhD and postdoc, Naomi has used her past experience as a teacher to partake in significant public engagement work and is engaged in considerable equality, diversity, and inclusion work promoting science to underrepresented groups. So the astrobiology fellows, myself, Collin Burnett, Vahab Raheji, Sarah Kingsley, Jose Ramirez Colon, and Nassif Muhammad are proud and excited to present our first speaker of the year, or of our academic year. And so, Naomi, I'll let you take it away.
Okay, thanks. I'll share my screen. Can you all see that and hear me okay?
Looks great.
Okay, great. Okay, so hi everyone. I'm so sorry I couldn't make it in person, but I'm really excited that I get to do this virtually anyway. And a big thanks to NSBP and also DPS. So you already gave a great introduction. I'll kind of skip over this quickly and say that I'm now based at NASA Goddard Space Flight Center. I moved out to Maryland in October 2021, and I'll talk more about what I've been doing in my current role as we go on. So I'll start right at the beginning. What is the JWST? So it's the largest and most powerful telescope we've ever sent to space. It has a 6.5 meter primary mirror made of 18 separate gold-plated movable segments, 4 scientific instruments that work in infrared wavelengths, a tennis court-sized 5-layer sun shield to keep it cool, and all of that was stuffed into a rocket and launched into space on Christmas Day of 2021. And then it slowly unfolded itself as it approached its home at the L2 Lagrangian point, 1.5 million kilometers away. So it's already done so much in just a year of science that it's had so far, and I'm excited to share some of it. And building it was also an international collaboration between NASA, the European Space Agency, including the UK, where I'm from, and the Canadian Space Agency. So a lot of people say that JWST is the successor to the Hubble Space Telescope, but that would be a kind of disservice to Hubble, because when it comes to space telescopes, Hubble is still the most famous example, although JWST is catching up slowly. Hubble launched in 1990, so it's been around a long time. It's actually 2 months older than me. And in that time, it's been a lot busier than I've been. It's done over 1.5 million observations, and it's produced beautiful images of the solar system, like the ones here. Here's some examples. These are examples of planetary images observed from Mars all the way through to Neptune, and some moons as well. And the JWST's mirror has an area more than 5 times greater than Hubble's, and Hubble and JWST really complement each other and have been working together very effectively over this year, which I'll demonstrate later. And it's more appropriate to call JWST the successor of Spitzer. So my PhD worked with the Spitzer Space Telescope, and it was launched in the same generation of telescopes as Hubble in 2003, and it was decommissioned only recently in January 2020. And it was in an Earth trailing orbit, and it was pretty small. Its mirror is less than 1 meter across, but it's more similar to JWST because of its wavelength range. So how is the JWST better than both of these older telescopes? How have we improved? So comparing them, the major difference is the size, and for telescopes, bigger always means better because we have a larger mirror, which means we have more photon collecting area, so we can look at dimmer and smaller and colder and more distant objects. And JWST's mirror, as I said, has an area of more than 5 times greater than Hubble's and more than 45 times greater than Spitzer's. And my favorite fact is actually that the Spitzer mirror is the same size as the secondary mirror on the JWST. So on the diagram of JWST, the secondary mirror is the one on the end of the boom that reflects the light back into the instrument. So that's the same size as the Spitzer primary mirror. And I already said the wavelength ranges are slightly different with all 3 of these observatories. Hubble sees from the UV through to the visible, through into the near infrared, so about 100 nanometers through to 1.8 microns. Spitzer saw from the near infrared through to the far infrared, so from 3.6 to 160 microns. And then JWST looks at kind of in the middle at near infrared through to the mid infrared at 0.6 to 28.5 5 microns. So for planetary science, this is useful because we can see through the hazes of the atmosphere, and we can see different altitudes and different features. We can see features in the right of this Jupiter image that's in the near infrared for JWST that are either invisible or more difficult to see in the left visible Hubble image. But both images are useful for looking at different things, so they work very well together. And the JWST wavelengths also overlap with both the Hubble and the Spitzer, so we get like a little filling of a gap, and it also makes it even more relevant for us to compare to these two telescopes in answering questions brought about by the telescopes. So how does a space telescope like the JWST work? The main job of any telescope is to look at faraway things. And JWST gathers light from these distant objects and focuses it into its multiple instruments that are housed behind its mirror. And those 18 segments that are all able to move completely independently, it means we can adjust the focus remotely at any time. And once that light's focused into the instruments, JWST stores that observational data before transmitting it back to Earth, and we receive it via the DSN, or the Deep Space Network, and that's a number of huge dishes located around the world. And when they receive this data, they send it through to the Space Telescope Science Institute, which is located near here in Baltimore, and they process and store it and distribute it to scientists all around the world. So anyone can access a lot of this data. So the 4 main instruments aboard, they're all housed in that integrated science instrument module, the ICEM, that's that big box behind the mirror. And we have the fine guidance sensor, or the near infrared imager and slitless spectrograph, or the FGS NIRISS. It's kind of a 2-in-1 instrument. We have the near infrared camera, or NIRCam, the near infrared spectrograph, or NIRSpec, and the mid infrared instrument MIRI. And you'll notice that 3 of these instruments operate in the near infrared, and MIRI is the only one working at longer wavelengths in the mid infrared. But these instruments provide imaging and spectroscopic capabilities across this whole spectral range. So imaging capabilities are kind of easier to understand and describe and kind of see what's going on. But what makes the JWST so powerful and exciting for scientists is its spectroscopic capabilities. So JWST has 6 different spectroscopic modes, but the main principle behind all of them is the usual spectroscopic principle. So splitting up light into these different wavelengths, measuring how much light there is at each wavelength, and that gives us a spectrum like the one shown above. So this is a simulated spectrum that shows the kinds of molecules that could be detected using a spectrum in the Eagle Nebula, so a star-forming region. And all 6 of these modes do a similar thing, but all slightly differently, and are used for observing different things. So I won't go into detail about all of them because I don't know the details about all of them, but the most exciting spectroscopic mode for solar system scientists is the IFU mode, or the integrated or integral field unit, or integrated field unit. And an IFU, it means a cross between imaging and spectroscopy. So best of both worlds. Each pixel in an IFU image has a unique spectrum associated with it. So this forms something called an image cube because it has 3 dimensions of information. And we'll see how useful that is for planetary science in a moment. So when we think of JWST, we think of astrophysics and cosmology and these distant galaxies and the Big Bang. And really, the JWST has these 4 major science themes. So the first one, first light. So that's looking back over the 13.5 billion years to see those first stars and galaxies forming in the early universe. And then we have galaxies, so helping us to understand how galaxies assemble over billions of years. And then the third one, we're seeing through the dust to look at these stars and planetary systems. So these beautiful nebula pictures that are everyone's phone backgrounds. They're even my background. And then the 4th one, when we think of this last one, a lot of people immediately think exoplanets, but there's no better way to understand how planetary systems work than by looking at our own planetary system. And solar system science with JWST is a large and very important area, with around 7% of JWST's first year of observations devoted to our own solar system. So what can the JWST look at in our solar system? What it have the ability to look at? And it can observe everything from Mars out. So planets, moons, asteroids, Kuiper Belt objects, comets. It's fair game as long as that sun shield remains in the correct place to protect the instruments from the heat of the sun. And it's actually more difficult than it sounds. It had to be theorized from very early on in the telescope's production. And when it's primarily looking at distant objects like stars and galaxies, stars being so distant means that they're relatively dim and also stationary on the night sky. And everything in the solar system in comparison is extremely bright and extremely fast moving. So engineers had to overcome these obstacles to make solar system science possible. So to get the observatory ready to do its job, we had to go through a process called commissioning, where we get everything working, how it was designed to work. And JWST had 3 phases that happened over 6 months. So the first phase was the spacecraft commissioning, which meant launch, deployment, and the beginning of us cooling everything to operating temperatures. Then the second phase was the telescope commissioning, so aligning the mirrors and all the other optics so we can get clear images. Then the third phase was the scientific instrument commissioning, so making sure those 4 instruments were calibrated and characterized and everything was working the way it should. And all of this was completed just over a year ago in July of 2022. So that's why we're kind of celebrating a year of JWST science, because it's a year since the commissioning ended. So this image shows all 4 of the instruments with their light successfully focused and ready for that third and last instrument commissioning phase to begin. And for this phase, I was part of a team led by astronomers at Space Telescope Science Institute, so that place in Baltimore, that did a part of this process. And we did 2 things that are important for solar system observations: moving target testing, or MT testing, and that made sure that JWST can track these objects moving quickly, and scattered light testing to make sure the instruments don't break when they look at something bright. So for MT testing, to observe objects in the solar system, we need the whole observatory to change its pointing direction relative to the background guide stars during the observation. So we had to test this capability by observing asteroids of different apparent speeds using each instrument and instrument mode. And so these images here are asteroids we observed for the testing, or some of them. And our initial speed limit that we had, or the limit that we initially thought JWST could handle, was 30 milliarc seconds per second, which is an angular speed. And you can see the one in the middle is traveling over twice that limit. So we can still successfully track it because you can see it in that bottom left quadrant. So the observatory is tracking it perfectly. And as a result of all this success, we are able to increase the speed limit for future observations. And I'll show a really great example of that in a minute. So the other type of testing was scattered light testing. So we wanted to answer some fundamental questions about the observatory. What happens if the telescope looks at a bright source? Can all the functions still work? Will all the instruments still produce images? And we tested all of these questions and happened to get these Jupiter images. And these were the first images of a planet with JWST that we ever got, and they shocked everyone. The rings of Jupiter are really not an easy thing to image, and here we did it with just an instrument test. So it was a really great sign of the planetary science to come. My boss actually showed me these images in the pub one night, and I almost cried. So my main job with JWST is to support the solar system scientists who have used JWST in the GTO program. So the GTO program is the Guaranteed Time Observation Program. And these programs are awarded to the scientists that contributed significantly to the design and management of key hardware and software components of the JWST, and or helped plan the observatory's scientific mission. So Heidi Hamel is the scientist that was awarded the time that she chose to use for solar system science of all kinds. And she's now one of my supervisors. And myself and my colleague Ian work on this. We're kind of on opposite sides, but doing the same job. So I work on everything planetary and Ian works on everything small bodies. So each of these bullet points is a program that has a team or multiple teams of scientists from many different institutions all around the world who looked at their target in this first year of JWST operations. And I work with those scientists in getting them from the raw data all the way through to publication of their scientific findings. So Ian's area is small bodies. They're of huge scientific interest because they're the leftovers from the formation of the solar system. We're using them to try and answer our biggest questions about the early solar system and planet formation. And they might even be able to tell us, give us clues about the origins of life on Earth. And I'll be going through some of these examples in detail in a minute. And this is my area. We get the best pictures, of course, and we can get a better understanding of how different types of planets and their unique systems are formed throughout the universe. We want to know about planetary atmospheres. We want to know about clouds. We want to know about surfaces, interiors, weather, composition. We also want to look at their moons and their rings and their smaller satellites and satellite systems to better understand their formation and their evolution. And we're always looking for signs of life anywhere we can, especially on rocky and icy bodies. And that's where spectroscopy really comes in handy with these objects. So the solar system seems like quite a small place when thinking on a cosmological scale, and the distances of other galaxies, but it's a pretty vast place to explore with a lot of diversity and a lot of different types of objects to look at. So this diagram is not to scale at all, and I'm going to talk in terms of AU when I talk about these distances. So 1 AU is equivalent to 93 million miles, or the average distance of the Sun to the Earth. And the Kuiper belt, for comparison, beyond Neptune is at around 30 to 55 times that distance. So now I'm going to kind of show you what the JWST has been doing this year, because it's been extremely busy, and I'm going to organize this mostly by distance, so starting close to Earth and going out. So we'll start with the closest objects to Earth, or near-Earth objects, very handily named, or NEOs. And a small body is considered to be an NEO only when it's at 1.3 AU or closer. And a great example is the asteroid system of Didymos and Dimorphos. So Dimorphos is orbiting around the larger Didymos, and JWST wanted to observe these two rocks in particular because they would the target of the Double Asteroid Redirect Test, or the DART mission. And DART's aim was to check if we can alter the trajectory of an object in case something ever comes towards Earth. And what DART did was it hit the smaller Dimorphos, and this image on the right is a time lapse of 5 hours that shows the impact of DART from JWST. And this was a huge feat for us in the MT test team because DART was traveling at 110 milliarc seconds per second, which is over 3 times that initial tracking speed limit. So only after that extensive testing and commissioning was this observation made possible. So another important milestone was hit with DART, pun intended, and it marked the first time that JWST and Hubble simultaneously observed the same celestial target. So the images in blue here are from Hubble, the images in the back are taken at almost exactly the same time. And the one in the front here was taken 12 days after the impact. And images like this helped scientists to come to the conclusion that the mission was a success and that we did, in fact, alter the orbit of Dimorphos. And this marks humanity's first time purposefully changing the motion of a celestial object and the first full-scale demonstration of asteroid deflection technology for planetary defense. And scientists are also very interested in the ejected material that's coming out. So the tail that you can see in that front image, they've been studying how it moves in space and its composition in order to better understand the inner workings of all these small bodies. So taking spectra of the tail to kind of see what's happening inside, because it's not every day that we get to see a fresh collision in our solar system. So out at 1.5 AU, we come to our planetary neighbor Mars, and we have a lot of landers and orbiters at Mars, but we need JWST to kind of take a step back and take a global perspective, especially at these wavelengths that we don't usually get to look at. And JWST took these maps back in September last year. And this left image shows a surface reference map with two NIRCam instruments field of views over the top. And the near-infrared images from JWST are on the right. So Mars is one of the brightest objects that JWST is allowed to look at. So it really was an amazing achievement to get these images. And the other people who were looking at Jupiter and some other objects that are just as bright were very relieved to know that if we can look at Mars, we're going to be okay with some of these other objects. And we also use NIRSpec to do spectroscopy at Mars. So this is a spectrum from 1 micron through to 5 microns, almost the full near-infrared capability of JWST. And the shorter wavelengths, so shorter than 3 microns, it's a little bit brighter where the spectrum is dominated by reflected sunlight. And then longer than 3 microns, we go further into the infrared, and therefore we're looking at more thermal emission. And we can see the bumps and the dips that show that we have detected carbon dioxide, carbon monoxide, and even some water. And this tells us about the dust and the icy clouds and what kind of rocks are on the planet's surface and the composition of the atmosphere. So lots of information to get from these spectra. And asteroids are made of metals and rocks, where comets are mostly ice and dust and have that characteristic coma or tail. So comets aren't usually found in the main belt because it's warm, and we thought water ice would kind of melt there. But main belt comet 238P Reed shows us something pretty unexpected. So on the left is an artist's illustration of what it might look like with all that ice and dust vaporizing because of the heat of the sun, because this thing's so close to the sun. And on the right is the actual JWST image and the spectrum as well. And the image shows us that distinctive halo and tail that makes it a comet. And the spectrum shows us that there is water vapor present. And scientists are trying to figure out how comets like this even exist. And this also marks the first time that a gas has been confirmed at a main belt comet. So Jupiter is the largest and one of the brightest and most challenging objects to observe with JWST. So a team of scientists called the ERS, or the Early Release Science Team, have got the job of testing all of the instruments and all of the modes on Jupiter's whole system. So they're testing JWST's science capabilities in the solar system and helping all of the other teams that we're supervising. And that's where these images come from. So the team has been characterizing Jupiter's cloud layers, the winds, the composition, the temperature structure, and even its auroral activity. And it's characterized the rings and the smaller moons as well. And this is some of the ERS team's most recent work on some of Jupiter's larger moons. So Ganymede, the largest Galilean moon's on the left, and Io, which is most volcanically active, that's on the right. And the top images are some close-ups from the Galileo and Juno missions, and the bottom images are from JWST. So that's a spectroscopic map of Ganymede on the bottom left, and it shows the light absorption around the poles that's characteristic of the molecule hydrogen peroxide. And hydrogen peroxide is a result of charged particles around Jupiter and Ganymede impacting the ice that covers the moon. And on the right, that's an infrared image of Io, showing several ongoing hot volcanic eruptions. So that central really bright one is at Kanehekili Fluctus, and the one on the right is Loki Patera. And this is the first time we were able to link volcanic eruptions to forbidden transitions of gaseous sulfur monoxide, so this excited form of SO. And these are from two separate publications that have very, very recently come out. So going out to 9.5 AU, we arrive at Saturn. So this NIRCam image is targeting the whole Saturn system. So we can look at the rings, the smaller moons, and the atmosphere. And although the Cassini spacecraft observed the atmosphere from closer up, this is the first time they're able to look at this particular wavelength at 3.23 microns. So this is unique to JWST, and scientists are still trying to figure out why there's that dark feature at its pole. And they're also using the long exposures of this image to look at the fainter, more diffuse rings, because Saturn is the king of rings. So what about Saturn's largest moon, Titan? Titan is the only moon in the solar system where there's a dense atmosphere, and it's the only body where there are rivers, lakes, oceans like on Earth, but they're made of methane instead of water. So Titan had this amazing press release with these two left images from JWST NIRCam on the left. It shows one filter highlighting the atmosphere, and the right one shows a composite of different filters. So we can see clouds and the albedo changes on the surface, and even lakes. Kraken Mare is thought to be a methane sea, and Belette is composed of dark-colored sand dunes. So the most exciting thing for the scientists that at least I was talking to is the clouds. So after seeing these clouds, scientists really wanted to look again to see if they were still there or if they disappeared. So 30 hours later, they used the Keck telescope. So this right image is from that observation and shows that the clouds are still there, but they've changed in shape a bit. And it's always helpful to get multiple observations at different times, but it's especially helpful when a body is so dynamic and active, like Titan and the other atmospheres in the solar system, because it's constantly changing. So another one of Saturn's large moons is Enceladus, and we put it in the same group as the Galilean moon Europa, as being an ocean world because they're cold, but we think they have these deep subsurface oceans that may contain life. And scientists use JWST recently, and they discovered this giant plume jetting out of the south pole of Enceladus, and it extends more than 40 times the size of the moon itself. And this animation shows how the plume feeds the moon's torus, and it has been estimated that roughly only 30% of the water stays within this water donut around the planet. And the other 70% escapes to supply the rest of the Saturnian water, like system water. So how do we know it's water? This is where the IFU capability comes in. So we use the near-spec IFU, and we use it to isolate the pixels that have the plume. So it's highlighted here in purple. So when we extract the spectra from just those pixels, we see those obvious water features. And those features are concentrated in the plume and not at the actual moon or in the background torus section. And that's how we now suspect a lot more water in the Saturnian system comes from these plumes and leaves this giant torus around the planet. So centaurs, in irregular orbits between Jupiter and Neptune, you sometimes get these weird things. They're half comet and half asteroid, and they're named centaurs because the mythological centaur is a half human, half horse. I don't know who came up with that, but it's great. So past Saturn, but before we reach our ice giants, we run into the Centaur Chariklo at around 13 to 18 AU. And what was so special about this one that we wanted to look at it with JWST, it was because it went through an occultation. And even though it's only 160 miles across, it has rings. And an occultation is like how we study exoplanets, very similar to that. So an object travels between us and a star, and it allows us to measure the light from the block star to find out more about the object. And so the left video shows Chariklo moving across that star in the center. And the right graphic shows what happened to the star's light. And you can see how close it was. We unfortunately didn't get an actual occultation of Chariklo, but we did get an occultation of its two very distinct rings. So we get two dips in that light, showing that it has two rings around this very small object, which is amazing. And shortly after that occultation, JWST also captured a spectrum with near spec of the whole Chariklo system. And this spectrum showed the presence of crystalline water ice, which has only ever been hinted at before with ground-based observations. And this is really redefining the different classes of small bodies in the solar system and showing us that even though things might be considered small bodies, they can still have very complex planet-like features like rings and moons. So we've looked at most of these objects now, but of course, my favorites are Uranus and Neptune, so I'm going to spend a little bit more time on them. My thesis used used Spitzer to look at Uranus and Neptune, and I looked at mid-infrared spectra of the planets and used radiative transfer analysis and optimal estimation retrieval to try and figure out what's happening in their atmospheres, so temperatures, chemistry, circulation, vertical profiles. So I'll talk a little bit more about this in a second, but this was all in preparation for JWST before it launched. So why did I pick Uranus and Neptune for my PhD? I could have picked any planet. It wasn't just because they were beautiful, it was because we know very little about them. And in this graphic here, all of the lines that you can see are where we've actually sent a mission. And you can see that Uranus and Neptune are extremely lonely because we've only visited them once with Voyager 2 in the late 1980s. And we did a flyby of Uranus in 1986 and one of Neptune in 1989, and that's it. We haven't been back since, but hopefully that will change in the near future. So when JWST finally set its sights on them, it was a very, very exciting time. And Uranus is my favorite. It's out at 20 AU, and it's my favorite because it's the weirdo of the solar system. It's the only planet tilted on its side. It also appears to be much colder than it should, colder than Neptune, even though Neptune's further away from the sun. And this image is a 2-color composite from February. And it's not actually a GTO program. These images were taken as an outreach-only program, so not for science purposes, but just to showcase the capabilities of NIRCam to everyone. And we looked at the planet for a total of just 430 seconds. And it's amazing that we can still see rings, moons, clouds, all beautifully clearly. And it wasn't on purpose that we only looked for 430 seconds. It was actually that the observation mostly failed. And we're still waiting for a secondary observation, but we still had enough to do a press release with all of this, which is really amazing. And there's still a lot that can be done with these images. We can actually get hints of the kinds of exciting things to expect in the future. If we zoom into this, we can see blurs in a lot of the places we expect to see the smaller moons. And scientists are already starting to delve into this data a bit more to try and look closely at those moons. And they're trying to look in detail at the rings and also trying to observe more distant, faint rings as well. And we see a lot of detail in the atmosphere on the right. So the cloud features tell us a lot about circulation, weather, deep chemistry, and the faint polar structure that you can see usually needs a lot of exposure time and processing to see using other telescopes. So it's amazing that we can just see it with this failed observation. And if we keep going out to Neptune at 30 AU, so this observation did not fail. This was a success. And this was the first time we pointed JWST at an ice giant. So it was the most exciting day for me in the past year. So you can see Neptune with its amazing rings and its largest moon, Triton, and the planet being on the background of galaxies, you really get a sense of scale of our solar system compared to the rest of the universe. And I was a subject matter expert for this and the Uranus image that I just showed. And as subject matter expert, I worked with a team at Space Telescope to get it ready for public release. So I helped with getting the raw data ready to send to the artists, where they made these composites. And I also researched and presented to the artists and writers what was interesting and new and exciting that they could put in their press release. And remember, we're all the way out at 30 AU. So the time it takes for Neptune to go around the sun is 164 Earth years. And it's actually so distant that this fact always blows my mind, that in the time that modern telescopes have been invented, that we've been able to actually observe Neptune, we've not seen enough time pass for us to view the North Pole. We've never seen it. We don't know what the North Pole looks like, which just is mind-blowing. So that's the kind of distances we're working with. And when I first saw this image, I didn't even think I was looking at Neptune, because we hadn't seen the rings like this since the 80s during the flyby with Voyager 2. So I thought that somebody had accidentally sent me a Saturn image rather than a Neptune image. And we've got 7 of 8 of the moons that are in the field of view labeled on the diagram. And in the atmosphere, we can also see lots of features. And scientists still don't fully understand everything we're seeing, because it's at wavelengths we haven't really looked at before. So they're still trying to digest and figure out what's going on. And then we have Triton, Neptune's largest moon in that top corner. And that's actually got its own program, completely independent of this, because it's actually considered a small body, because we think it's a captured Kuiper Belt object rather than a natural moon. So it has a lot more attention from the small body community. Then some other details you may have missed in these. Not only can we see the rings, but we can see these faint features, which are called ring arcs in the top left there. And we can also see the faint inner Gale ring. And Naiad, the moon, is visible, and it's only 60 kilometers in diameter. So even at this short exposure at 30 AU, we're still able to see something 60 kilometers in diameter. It's really quite astounding. And the right image here, the 2 images, they show the atmosphere at 2 wavelengths. And we can see the brighter areas are methane clouds, so reflected sunlight, and the darker areas are looking deeper at methane emission. And scientists are still kind of using these images to do science, even though they were just meant for outreach. There's a lot of papers, I think, trying to use these for their scientific outcomes. So these first ice giant images have all been taken with NIRCam. So for the GTO, we kind of want to use MIRI and NIRSpec more because of their IFU capabilities and spectroscopic capabilities. And the mid-infrared especially is exciting because it's so hard to observe from Earth, because things like water vapor especially block a lot of the mid-infrared wavelengths we want to see. We only get very small windows to see through the atmosphere from the ground. So why is the mid-infrared useful in particular for these planets? These are some example images of Uranus from visible through to the microwave. And we can also apply this same vertical profile to Neptune. And these different wavelengths are sensitive to different depths in the atmosphere. So on the right, this shows that vertical structure of a typical ice giant atmosphere. So we're showing the stratosphere and the troposphere below, separated by the tropopause. And we see where each of these wavelength bands senses, or where it's sensitive to. The visible and the near infrared in purple and blue. So like Hubble Space Telescope or some ground-based telescopes, we kind of sense mostly the cloud tops, the tops of these tropospheric hazes. And the microwave goes deeper into the troposphere, but with the thermal or the mid-infrared, we can sense both the stratosphere and the upper troposphere, which is extremely useful because these depths are what we call the middle atmosphere. It's the stratosphere and down to around 2 bars of pressure in the upper troposphere. So these images are Uranus at 2 different mid-infrared bands from the Very Large Telescope, or the VLT, Vizier instrument. And we see a different structure of the troposphere compared to the stratosphere. The stratosphere contains complex hydrocarbons that we're very interested in. These hydrocarbon hazes dominate stratospheric processes. So when methane is elevated into the stratosphere, it's broken down into component forms by photolysis or photodissociation from the sun, and reforms into complex hydrocarbons like acetylene and ethane, ethylene, all of these. And observing these species tells us a lot about the chemistry and the vertical processes of the atmosphere. So the mid-infrared was a main motivation for using Spitzer and JWST to look at both of the ice giants. This is some of Spitzer spectra. So Spitzer was used to observe both ice giants between 2004 and 2007, when it was still in its cold phase. And because the mirror is so tiny, we can't get any images, none at all. We're treating both planets like point sources, and we just get spectra, globally average spectra. So this is an example from 2007 equinox of Uranus and the 2005 of Neptune. And we use these spectra in our radiative transfer and retrieval models to find out what the atmosphere is made of, what the temperature is at different depths, and how things change, the chemistry, etc., how they change at different depths. And that can even give us clues about weather and circulation and deeper chemistry as well. So we used to have to kind of choose between getting information like spectra with Spitzer and images with ground-based telescopes, but with the JWST, we can get both using that IFU technology, so we can really see how that's so powerful, especially at these wavelengths. And one of my favorite facts is that because each of the pixels has a spectra, they're actually called spaxels, which is my favorite science word at the moment. So for ice giants especially, getting these image cubes is extremely exciting. And I can't unfortunately show you some of these image cubes because they're still on their way to publication. But I can show you the models that we generated of them before launch and tell you that it looks extremely similar to this. Like I thought I was looking at a model when I saw the actual results. So the first observations of Uranus were actually with MIRI and NIRSPEC in January. And it allowed us to plan ahead for actual data analysis to make these models. So these are generated synthetic data cubes in the resolution and the wavelength range of the MIRI IFU. So the image is part of an example data cube, and then each pixel in the image is has a spectrum which is a similar resolution to the snippet that's above, and the resolution is actually a lot greater than the resolution of Spitzer. The highest spectral resolution of Spitzer was 600s, whereas the lowest resolution of JWST is in the thousands. So it's really exciting to get such great data. And I'm almost finished. So I'm PI of some Hubble time that is looking at both ice giants at around the same time as JWST. So we're using WFC3 UVIS instrument to do similar observations to the Hubble OPAL, or Outer Planet Atmospheres Legacy program. And it's exciting because we get these extra wavelengths into the visible band. We get dark spots of both planets, and they're only visible in blue wavelengths, and JWST doesn't have blue wavelengths. So it's really exciting that we can actually see them with Hubble and kind of look at the same time and see if there are any there. Also with the IFUs, we get a lot of information, but we sacrifice a little bit of detail, so we can get better detail from Hubble in the near infrared to identify smaller cloud features, for example. And the OPAL program has been observing these planets with Hubble since 2014. So we also add a little bit of temporal context when we compare things alongside this data set. And there are multiple programs that are observed alongside JWST for Uranus, actually. Other Hubble observations in the UV, XMM mutant, and Keck all got to look at the same time. So there's a really exciting data set about to be released. And it's seriously enhanced what JWST can do. And I didn't want to finish without mentioning Kuiper Belt objects, because the Kuiper Belt extends pretty far out to 55 AU, and these KBOs are much colder and further away than asteroids and comets. So this makes them harder to observe, but it also makes JWST's capabilities the most advantageous for them. So a lot of JWST time was devoted to Kuiper Belt objects, and I've lost count now because over 80 different Kuiper Belt objects have been observed in cycle 1, and this has allowed scientists to start classifying them in new ways and gain more information about their colors, sizes, compositions, and none of that was doable before JWST. So everything I just spoke about was in cycle 1 of JWST time, and cycle 2 technically started the beginning of July and goes until the same time next year, and a lot is planned in the solar system. So a lot more small bodies are going to be observed because there are so many, countless numbers, and Jupiter's upper atmosphere and aurora are going to be looked at more closely. The smaller moons of Jupiter and Saturn, there's also a lot of them to look at, a lot more that we haven't focused on. More ocean worlds, because people are very excited about moons like Europa and Enceladus, and a program where we're going to do near-cam maps of Uranus, similar to the outreach images, but with more time and filters specifically for science. And scientists are already writing proposals for cycle 3. So they have to write their plans and their justifications to use the telescope, and then a science panel then decides later this year who has the best ideas, and those are chosen as the next observations. So it's a stressful time for scientists right now, but it's also exciting. And look out for any news about the Uranus Orbiter and Probe, or UOP, or the next flagship mission, hopefully. So there was a decision to send to Uranus rather than Neptune, purely based on technology readiness. So because the distance of Neptune requires more advances and tech, the Uranus is ready now. So that's why they chose Uranus over Neptune. And the optimal launch window is actually soon. It's in the early 2030s, but that would mean that things start having to happen like in the next couple of years, which may not happen. So we'll see what the timeline looks like in the next few years. And we recently had a meeting in Pasadena to discuss the mission, and it's a great time for early career scientists and engineers to get involved. And this should start being a pretty regular thing, these kinds of meetings. So look out for any future ones and any early career travel grants that may be available, because they were for this meeting and they will be for future meetings. So yeah, thank you. I will leave you with the summary, and I'm happy to answer any questions.
Thank you so much, Dr. Rowe-Gurney, for an amazing talk. We're going to open the floor up to questions now. I believe Dr. Glass is going to be giving people speaking privileges. But while she's doing that, I can go ahead and read one of the questions in the chat. This is from Ashkar. He asks, what is the general process from getting raw data from JWST to getting these images on the slides?
Yeah, great question. So when it comes down from the JWST, it gets sent to Space Telescope, and they generate kind of an automatic pipeline, which gets kind of a standard image that maybe, so at the beginning, there were a lot of issues because it's still a new telescope, so they're constantly trying to figure out how to like fix things and like tweak things to make it perfect. And so when we get the data, we kind of go back to the raw data and process it ourselves using a pipeline. So the pipeline comes in a Python code, and you can tweak it and make it do things that you want it to do specifically. You can also add extra code to maybe add a dark here or delete a pixel here. And then once that comes out, you can kind of check it, calibrate it against something you know. So a lot of people with MIRI especially have been using Spitzer as a kind of baseline, kind of this is what we know is probably correct. JWST might improve upon it, but it won't completely change it, we hope. So they're kind of using that as a way to check the calibrations, and then from there we can kind of go further with the science.
Great. The next question is from Sarah, and she asks, does each pixel/spaxel contain their own spectroscopic data?
Yes, so every single pixel in the kind of images that I showed has its own unique spectrum. So for example, we can use this with ice giants. We can look at a cloud or a suspected storm, and we can get the pixel with that storm, and we can see whether there is a certain spike in the spectrum in that storm that isn't in the kind of background pixels. And we can see, okay, this storm is convective because it's got more acetylene in it, which means that there's more methane being pumped up, and more methane kind of breaking down into acetylene. So it's really, really helpful to be able to have these very unique spectra for each pixel.
Awesome. And I believe everyone has the ability to speak now. So everyone, if you have a question, feel free to unmute yourself.
Just try not to ask me too many questions about small bodies, because that is Ian's wheelhouse, not mine.
And the fellows are welcome to go ahead and ask questions if, oh, Micah's asking a question. Go ahead, Micah.
Oh, yeah, you can see me unmute. That's funny. Hi, yeah, Micah's here, research scientist here. Just wondering what sort of you can say about those really bright spots in the Neptune image. Like, were those clouds? Were those like some sort of atmospheric structure? I just thought that the really bright spots, it kind of reminded me as well of like a Saturn image where you've seen in the IR that there's these really bright spots sort of spread around Saturn with the rings around them. But I was surprised to see them so bright in the Neptune image.
Yes, so were we. We were very, very surprised that they were like, there was a point actually that one of these clouds saturated the filter, which we were not expecting to happen. And we're still trying to figure out why they are appearing so bright, but especially the ones on the edges, we are kind of attributing it to limb brightening. So at certain wavelengths, we're seeing either deeper or shallower into the, at certain emission angles, we're seeing it deeper or shallower into the atmosphere, and at certain points that will brighten at the edges. And we're kind of seeing that effect really double down with JWST because of how sensitive it is. Yeah, we weren't expecting them to be quite so bright as well. But they are clouds. They are methane clouds. Usually we associate them with dark spots, but actually with our Hubble data, we haven't seen any strong signs of dark spots. So it's another interesting conundrum.
Very interesting. Thanks so much.
Thank you.
I'll chime in here with a question if y'all can hear me. I was curious about, from my understanding for space telescopes, if there's like opportunistic, like big events to observe, time can kind of be redirected towards that. So I'm curious if there's any solar system events that you think would be deemed worthy to direct like JWST to in real time, like that you could confirm with another data set, like a dust storm on Mars or something. Is there anything that comes to mind for that opportunistic observing in the solar system?
Yes, great question. So you have to propose for these TOOs or targets of opportunity. So we have, I think, only one of them maybe 2 of them happening at the moment. So they kind of have bled over from cycle 1 into cycle 2, and they are for collisions. So things like the Shoemaker-Levy 9 collision. So it was an asteroid that hit Jupiter and stirred up a load of really exciting stuff in the atmosphere and kind of made an explosion on the planet. And that happening at any giant planet that we can observe, that is a target of opportunity that is currently active. That we're kind of also interstellar objects are also a thing for targets of opportunity. So what is it called? Oumuamua, the one that came that looks like a cigar. That was so things coming from way outside the solar system and just shooting in and then shooting out again. Anything like that happening is also a target of opportunity that we have time ready for. Obviously, they just kind of clear a schedule. I don't know who they kick out, but probably some galaxies or something, and make room for a target of opportunity like that. Great question. Thank you.
Oh, I hope there's targets of opportunity sometime during
Me too, me too. Still waiting.
Any other questions? Okay, I'm not hearing anything. So Collin, do you want to close things out and thank the speaker again?
Yeah, so thank you so much, Dr. Rowe-Gurney, for coming to speak to us today. We're sorry we couldn't have you in person, but we're glad we got all of the technology figured out and the YouTube live stream working.
Nice.
So again, thank you so much.
Thank you. Thanks everyone for coming.
Thank you so much. That was fantastic. I had no idea that so much solar system science was going on already with JWST. That's just phenomenal. So thank you so much on the tour of the solar system. Phenomenal talk.
No problem, no problem.
Got a lot of hearts and clapping, I see. And we will have this up on our website. And if anybody, I know there were some people, it sounds like they went to the room and couldn't find it online. So we're going to, Nassif, if you're online, we're going to do a deep work on posting this talk all over the place, right? So that everybody that didn't get a chance to see it live can now watch it online. So thank you. Thanks, Collin. Thanks all the fellows for organizing. And thanks, Naomi, so much for this fantastic talk.
Yeah, thank you.
Yeah, thanks so much.
Nice to meet you.
You too.
See you.
All right. Bye, everyone.